So when I look at a pile of data and I compute a standard deviation or a variance, if I'm just thinking about one variable from one item, I have this pile of data, I computed standard deviation. What does that tell me again about the data? Standard deviation or variance mean? With an adjective. Pictures of targets, right? Bullseyes. What did the variance mean? Spread. So if I have a small variance, a small spread, I get a more consistent result. When I have a large variance, I have a less consistent result. So volatility in quarterly returns for market funds, quality control, consistency in wait time. Your time to our next representative is beep 3 minutes. Get that on hold all the damn time, right? So smaller variance means a more consistent result. We're less spread out. So I can ask this same idea. Do I think the variance on data pile number 1 and the variance from data pile number 2 are substantially different? If I'm looking at 2 different market funds, I've got, I don't know, currency exchanges. If I'm thinking about dollars versus euro, that's one interesting level because the dollar and the euro are roughly similar in value. Anybody know the value of a ruble at the moment? Open up your technology and Google, how much is a ruble worth? Or a lira? Lira are fun ones. How much is a ruble worth?
0.012 of a dollar.
So just over a penny.
Yes.
A ruble is a penny. Well, I would expect then, if I was looking at prices in dollars and looking at prices in rubles, there should be a lot more spread in the prices in rubles. It'd be like I was measuring all my prices in pennies. It's a very different setup. So I want to measure variance, but I want to be able to take into account sizes. So let me think about a test that might do something like that. I could be asking, are these variances different? Do the variances sigma 1 squared and sigma 2 squared really differ? And if so, how? Again, there are 3 different versions of this, right? I could ask, is one of them bigger than the other? Or should they be equal? So I could ask, is sigma 1 squared bigger than or equal to sigma 2 squared? Or I could ask, is sigma 1 squared the same as sigma 2 squared? Or I could ask, is sigma 1 squared less than or equal to sigma 2 squared? Just like before when I was thinking about means, same idea, right? Well, if these are my null hypothesis statements, what are the alternate hypotheses that go with each one?
The other one is not equal. The other one is bigger than.
Now, the problem is that that doesn't give me a single value to compare to. I could subtract and compare these to 0, right? But a lot of people, instead of subtracting, actually wanted, instead of looking at these as absolute numbers, wanted to look at the ratios. So the other way to think of this is to do sigma 1 squared over sigma 2 squared. I want to rewrite all 6 of these sentences where I divide by sigma 2 squared. So H0 now becomes sigma 1 squared over sigma 2 squared is bigger than or equal to 1 or less than 1. And here it becomes sigma 1 squared over sigma 2 squared equals 1 or is not equal to 1. And then this third version, this one's tight, less than 1 or greater than 1. And again, my alternate hypothesis tells me about direction. This is a left tail, this is a two tail, and this is a right tail. So rather than think of these two and compare them to each other, I take the ratio and compare that. If my variances are similar, I would expect this number to be fairly close to 1. And that means, oh, wait a second, it means something else too. Notice everything in this entire fraction is always squared. Numbers that are squared have what sign? When you square a number, what sign does it get? It's positive, which means this number is never less than 0. Right away, I know I can't use a t distribution. I can't use a z distribution because those are bell curves that are centered at 0 and have a bunch of negatives. This thing is never going to be negative. Oh. So I definitely need to go back to my chapter on PDFs. And I need to look at all of the other PDFs that we didn't talk about. I have exponential PDFs. I have triangle PDFs. I have hypergeometric. There are all sorts of different functions I can create. But a guy by the name of Ronald Fisher investigated variance like this. And Fisher came up with a distribution that looks different. It's definitely lopsided. It's shifted to the left quite a bit and has this really long skew tail going out to the right. Since Ronald Fisher came up with this, this is called an F distribution. And Fisher said, the shape of this actually depends on 2 different things. It depends on the size of each of my groups, group 1 and group 2. So the graph looks something like this, but it changes based on 2 different degrees of freedom. Fortunately for me, degrees of freedom are still computed exactly the same way they were before. So I can say, oh, we're just going to use N1 minus 1 and N2 minus 1. Number of people in group 1, take away 1. Number of people in group 2, take away 1. And Fisher said, this distribution behaves the way variance should. Now, just as before, once I have a distribution, I notice that way over here on the left, that distribution gets really small, right? And way over here on the right, this distribution gets really small. So I can think it's really unlikely that I will see something down close to 0. And it's really unlikely that I'll see something way up there, close to, I don't know, 3, 4, 5. It's really unlikely to be way out on this end. It's really unlikely to be way down on this end. So I'm going to treat my test about variance the same way I treat my test about means. I think these variances are the same. That would be a two-tailed test. I compute some statistic, and I compare it to numbers from this picture. So, what statistic should I compute? What do I use to estimate sigma? If I want to know stuff about sigma 1 and sigma 2, what do I actually calculate? Back when we talked about estimators, minimum variance estimators, unbiased estimators. What did I use when I said I want to estimate sigma? That's a mean. That doesn't help me estimate my variance. That's something that goes with my variance, but it's not used to estimate my variance. What did we use to estimate mu? Oh, that's confidence interval. That's not my estimator itself. For mu, I used my sample. Right. I need to use my numbers because I don't know the whole population. So for mu, I would use X bar. For sigma, I'll use the standard deviation. So what Fisher said is what I want you to compute are calculated F value will be S1 squared and S2 squared because I don't know the population standard deviation. I only know for my little sample. By the way, you could just as easily write this S1 over S2 all squared. But 99.9% of the time, no matter where you look online or in other references, you're going to see it written this way. So I wanted to write the square on top and the square on bottom. So once I have this calculated value, let me think about what we were doing on Wednesday, what we're doing on Monday. Once I have a calculated value, what do I do when I'm doing a z-test or a t-test? And the critical value is determined by, in that case, but it's really determined by alpha, the size of the piece on each end that I want to cut off, right? If I'm doing a left only, then it'd just be the area on the left. If I'm doing a right only, it's just the area on the right. If it's a two-tail, then I split the area in half and put it on each side. I'm going to do the same thing. I'm just going to do it on this picture instead. So in exactly the same idea, I've got a critical value, but I've got two of them. Like with a two-tail test, but they're not the same number plus or minus. I have a left value and a right value, and they're different numbers because they're both positive. Remember, the F distribution is always positive. There's no negative numbers here. So this left thing, FL, or this right thing, FR, those are my critical values. But I need to know what alpha is, and I need to know my 2 degrees of freedom. I'm going to tell you right now, this is a calculus problem, and I do not do calculus in this course. Period. End of story. So how do I get these numbers?
Or Excel.
There are the commands right there. Literally, here's how I get this. F dot inverse. Tell me the F value that gives me the area I want. And if you want the F on the right, it's F inverse RT for right tail. Perfect. By the way, there is an entire F table in the back of the book. There are actually 3 different tables. Because look at this table, it's got degrees of freedom for both columns and rows, and then I have to tell you which alpha I'm using. So this is the one where alpha is 10%. This is the one where alpha is 5%. This is the one where alpha is 2.5%. Oh, crap. I need a different table for every different alpha. This is nauseating. What a pain in the neck. I don't like this. I would much rather use Excel to come up with my left value and my right value. But my decision is still the same. Reject the null hypothesis when you're in those rejection zones out on the tails. You're either way in here or way out there, depending on which kind of test you use. So I need to know, is my number that I calculated between or not? If it's outside, we're screwed. I will also tell you that the table in the back of the book is restricted to only giving me the right tail. There's a way to get left tails from right tails. If you have the right tail, it came with 2 numbers, right? Degrees of freedom 1, degrees of freedom 2. So I need to know what row and column I'm in. Row number for degrees of freedom 1, column number degrees of freedom 2. That's the way I always read this. But then I go look at the back of the book, and degrees of freedom 2 is the rows, and degrees of freedom 1 is the columns. Noise the hell out of me. It's my problem. I just need to know which one's which. To get the left one, I flip the degrees of freedom, and I take 1 over. So if you want to use the table in the back of the book, that's the way to use it. But I must tell you, I would rather use Excel at this point, or some other technology to get there from here. But I'm going to make my same decision once I have a rule and a statistic to work from. An example, so you don't just think I'm blowing smoke here. Problem number 31, page 31? No, problem number 37. Problem number 37. They're just giving me the actual summary data here. So I'm going to copy down the information that we were given. Page 398. Page 398, problem number 37. I am told in part A that group 1 has a standard deviation of 5.1, and there are 11 people in that group. Group 2 has a standard deviation of 3.2, and there are 8 people in that group. And I am going to use an alpha of 0.05, and I want to know if these are equal or not. So I'm going to do a two-tailed test. It told me explicitly to do this. Okay. Assuming I was going to do this with the textbook, because I'm doing a two-tailed test, I have to remember that half the area goes in each group. So if I were going to do this on a table or in Excel to find my numbers, I'm really thinking not about alpha being 0.05, two-tail, I should use alpha over 2, which is 0.025. Because that's what our little picture showed us, is that I want half the area down here and half the area up here. Okay. What is my null hypothesis in a two-tail test?
Your variance of the first one squared is not variance, or is equal to the variance of the second one squared.
My two variances are equal. Or that their ratio is equal to 1. And that means my alternate hypothesis is that they're different. Okay. I need 3 pieces of information now. I need a calculated value, and then I need my 2 critical values. And since I'm doing a two-tailed test, I'm thinking about this middle picture. I need to know what this number is, what this number is, and what's the number I come up with. So let's start with our calculated value, because I can do that without looking anything up anywhere. What's our calculated F value?
That's what one squared by the 3.2.
Or if you'd rather, you could factor that square out, right? 5.1 over 3.2 all squared. But what is this number?
I just,
Yes, substantially. 2.54. Good enough. Okay. Now I need edges. I need my critical values. Appendix F. I want 0.25 because it's half. Now, how many people were in the first group? So degrees of freedom for the first group is? Degrees of freedom for the first group is 10. How many people in the second group? So the degrees of freedom for the second group, 1, 2, 3, 4, 5, 6, 7. Oh, I'm in the wrong table. Back up. 025. There it is. 10, 7. Write this number down, 4.76. That's the right one. FR. Now, how do I get the left one?
Have to go 7, 10.
Okay, so now I go back to my table and I go to the column for 7, because that's 1, degrees of freedom 1, down to 10, and I get 1 over 3.95. Jason, what's that number? Okay. Now I ask the question. What's my decision based on my calculated values versus my critical values? Should I reject my null hypothesis? Why not? Aha! It's between. The rejection zones are not between. I'm in the middle. I'm in that unshaded section. Do not reject. Since my left value is smaller than my calculated value is smaller than my right value, I do not reject my null hypothesis. Which means, as far as I can tell, there is no way to say these variances are different. Statistically, numerically, clearly they're different. 5.1 is not the same as 3.2, but because of the two sizes of the groups and the amount of internal variation I could have, I don't know that there's a reason for one of these to be substantially different than the other. Questions? I hate this table. There are like 7 pages of table here for all the different degrees of freedom and the different set of, screw it. Here's Excel. Nice big empty book. I want f.inv. I want the area. How big is the area in my left tail? Alpha over 2. 0.025, comma, degrees of freedom 1 was 10. Degrees of freedom 2 was how much? 7. Close my parentheses. There's my 0.253. Right tail equals f.inv.rt. Everything else is the same. I don't have to switch the things here. I only have to switch them when I use the table. I don't have to switch them in Excel. So 0.025, comma 10, comma 7. And there is my 4.76. Yes, ma'am.
Put it into the calculator and use the value to decide if it's in there as well.
Stats. Stats. Tests. There it is. 2-sample F test. And I can give it the statistics and ask, do I want to do a 2, a left or a right? I wanted to do a 2. There are my numbers. You'll notice it gives me the same F value, 2.54. It doesn't give me the critical values. It instead gives me a p-value. Hallelujah. When do I reject for a p-value?
It's smaller than the 2.5.
Unfortunately, no. It's not smaller than the 2.5. It's smaller than
The 0.
the significance. But the significance itself is 0.05, not 0.025. Or we would have to multiply by 2.
So we don't look at just the
Right, because that's 1. And in this case, it's a 2-tail, so I need to double that. So I double the 0.025. That's bigger than 0.05. I do not reject. I only reject if it's smaller than. Thank you. There is an arrow here. That arrow takes me down and shows me the other number of participants, just to make sure I typed everything else incorrectly. It's possible that I would have messed that up. If you are given actual data, wrong one. Here, you have to put that data in the list piles. So if we do list, see how it says above the stat, it says lists? You can actually just type stat edit. There are your lists. And you put the first group in list 1, the second group in list 2, and it'll do all the standard deviation calculations for you. It did that in our descriptive statistics, right? So we know the calculator knows those routines. It just runs them in the background, does all the work. I really like that part. Number crunching is the easy part. Let the computer do the damn work. I have to be able to figure out what it says. Questions? I did the same calculations here because there's a part B and a part C to that question. But in part B, they only give me a 1-tail test. It says use a left tail. So I only needed FL. In part C, I only needed FR because it said do a right tail test. You go way too. However, here in problem 39, I'm asking about a drill. I have a drill hole, a drill that goes through sheet metal, and it's supposed to make 0.5 centimeter diameter holes. I buy a new drill press. I measure a dozen parts for the old drill and the new drill. Is the new drill more consistent than the old drill or not? Now, again, I've got all the data here. So I don't need to do the actual calculation part, but I have to start with a question. What should I be testing? So let's read through the question one more time. New manufacturing process, a new process drills holes in sheet metal supposed to be 0.5 centimeter in diameter. Before and after a new drill press is installed, the hole diameter is carefully measured in centimeters for 12 randomly chosen parts. At alpha equals 0.05, do these independent random samples prove that the new process has smaller variance? What kind of a test? A right tail, a left tail, a true tail? Maybe I should ask another way. We said, does the new drill have a smaller variance than the old drill, right? So I want to know, is sigma squared for the new drill less than sigma squared for the old drill? Now I go back and I look at my data. And my data is explicitly listed with which one first? The new drill. That means that's going to be sigma 1. So really, that's going to be my alternate hypothesis. This is going to be H1. And if that's true, what's H0? Now, again, I'm pedantic here. I'm going to write these as ratios. So I think of this as sigma 1 squared over sigma 2 squared being less than 1. And this being sigma 1 squared over sigma 2 squared is bigger than or equal to 1. My alternate hypothesis tells me which kind of a test it is. Is this a right, a left, or a 2? A left, because we're to the left of 1. All of this is done before you do any actual calculation. You need to come up with the question you are trying to answer before you type a single number, before you just do anything with your calculator at all. You need to know what's the question you're asking. Oop, I didn't pull it up. Let's pull it up. Cancel that. Here's our data. New drill on the left, old drill on the right, so I can use it as column 1 and column 2. That works. Wait a minute. All of my calculations done by Excel were done under the data pile. And if I go to the data analysis, there are t-tests. If I scroll down, there's a z-test. Oh, there it is. F-test. 2 sample for variance. So let's hit that. Variable 1 is the new drill. Variable 2 is the old drill. I highlighted the labels, so I'm going to click the labels. And I gave it an alpha of 0.05 because that's what it asked me for in the problem. And I want to let it do all the work and spit out a pile of numbers for me on a new page. So I clicked new worksheet. Book. Here's my answer. Now, since these are really small numbers, the actual variance is a very small number. E to the minus 6 means that's multiplied by 10 to the minus 6. That's in millionths of centimeters. That's a tiny itty bitty number. But my calculated F value is right here. Boink. Now use either of the numbers below that. Should I reject my null hypothesis?
Yeah, check the order. Look at the left tail.
I'm looking at left tail, the number's smaller. What's more, look at the p-value here. The p-value in this case is 0.0003. I want it to be less than 0.05. That's a lot less than 0.05, isn't it? That's strong evidence, statistically, that this new drill is more consistent than the old drill.
Question this, so the p-value,
Mhm.
is p-value at no matter what, it's just about the alpha, it's just about the significance.
Right.
So it doesn't matter if it's two-tailed, it's just.
Well, if it's two-tail, I need to multiply that number by 2.
Ah.
And that's why it says next to it P one tail. So if I was doing a two-tail, I'd have to double that because there's a chance it could be down here, a chance it could be up here. Now, let's look at the actual variance. The actual variance here the variance for the old drill is 0.00003. The variance for the new drill is 0.000000. There's an extra 3. The new drill has a variance 1/10 of the size of the old drill. I've improved by a whole order of magnitude here. The variance is substantially smaller on the new drill than the old drill. Now, I don't know how much this new drill press cost you for your sheet metal hole punching business. I don't know how expensive that kind of a drill press is. I don't know how much this piece of sheet metal that you are putting holes in is worth. What are you building it for? That this tolerance has to be this close. At some point, you replace the drill, right? Anybody done any sheet metal work? I hate working in sheet metal. My drill always skitters off, but I don't have a drill press. I don't have a hand drill. So the longer you use a drill bit like that, the duller it gets, the more the cutting edges are damaged, the more possibility there is for that to tear instead of cutting. That's a bad thing. Perhaps this particular piece of sheet metal is going to be used as a plate in a bridge. Perhaps it's going to be used as a screw hole plate on a bone repair, like they put pins and plates into people's legs. I want to know how close this is going to be. There's statistically significant, and there's practically important. How important is it for me to get this hole to be 1/2 centimeter? I would also point out to you that they only gave me one critical value. And they didn't give me an option to do a two-tail or a one-tail. They only gave me one critical value. What the fuck? What happened to my other critical value? It's my choice of which is group 1 and which is group 2 that tells me whether I'm going to do a left tail, a right tail, or a two-tail. If I'd switched the new drill and the old drill columns, then I'd be doing a right tail instead of a left tail, wouldn't I? What if I say no, regardless of which way I want to do it, I'm always going to set it up so that the group with the larger standard deviation, the larger variance, is on top. So instead of using S1 and S2, I'm going to write S max and S min. Whichever one is bigger, that one goes on top. Then I only ever need to do one kind of test. And it turns out it's a right tail. This is referred to as a folded t-test. Sorry, folded f-test. And that makes the table a little bit easier to do, a little easier to deal with. It means that I'm always looking on the right, always. But by this folding behavior, it changes just my application of the table. I get all sorts of twitchy when I see shortcuts like this, especially because Excel gives me the p-value. And that's a more reliable method in my head. I don't have to remember which way I'm going. I just know if my p-value is small, I'm rejecting. I think that's more useful. But we are talking about examinations of variance, right? I'm looking at how much spread there was in group 1 versus group 2. What happens if I have more groups? We did one sample hypothesis test. Here's your one pile of data. Does it meet my benchmark or not? We did 2. How do they compare to each other? What if I've got 4 groups? I've got freshman, sophomore, junior, senior students. I want to compare study hours between all of them. Oh, well, grad students too, right? How much time do people spend studying? And I could even do this with a documentation. They're taking this class. They need to review these things online. How long are they online? Every day. I can check. Not going to do self-reporting data. That's always biased. I'm not going to survey you all. I'm going to measure how often my students in this class, and I'll check the sophomores, the seniors, the juniors, freshmen, and do a comparison between all of them. I don't want to do this 6 times. Freshman, sophomore, freshman, junior, freshman, senior, sophomore, junior, sophomore, senior, junior, senior. No. No, there's got to be a better way. Guess what we're going to start talking about on Monday? But this ends chapter 10. And that means 8, 9, and 10, 3 chapters, that's an exam. A week from today, unfortunately, I'm still in the process of writing your review sheet, so it should go up over the weekend. But that means the homework for this is due Wednesday. I will see you all then. Have a wonderful